Okay, so next we're going to do heat and temperature. So first we're going to have to describe the difference between temperature and heat. So you look at the thermometer and it tells you what the temperature is. Temperature is just a measure of how hot something is or how cold something is. Heat is the energy that is in that body. Temperature measures heat. So heat is a form of energy that causes a temperature increase when you add it. So you turn on the oven, you're adding heat, you're increasing the temperature. You open the fridge is decreasing the temperature because it's removing heat. So in physics, we use a different scale to Celsius. The scale we use is called Kelvin Scale, and we have a defining zero. So we have a 0 in Celsius, but we also have a 0 in Kelvin. Now 0 Kelvin is minus 273.15 Celsius. So that means if you want to get a temperature in Kelvin, then you just get the temperature in Celsius and take away 273. Temperature in Kelvin is going to be the temperature in Celsius plus 273.15. So the Kelvin temperature of 20 degrees is going to be 293.15. Okay. 0 Kelvin denotes absolute zero. So at that point, there's literally no energy whatsoever in that body. So that means there's no molecules moving around because of heat at all. The next thing we're going to talk about is heat capacity. Okay, so heat capacity is the heat energy that you need to put into something to increase its temperature by 1 Kelvin. Changing 1 Kelvin is the same as changing 1 Celsius. So the difference between heat capacity and the other thing we deal with in physics called specific heat capacity is that specific heat capacity is the amount of energy you need to change a kilo of a substance by 1 Kelvin. Apologies. So then thermometric properties is another definition you need to know. So they're physical properties that change measurably with temperature. So the temperature goes up, the length of the column of mercury in the thermometer gets longer. The temperature goes down, the length decreases. So a standard thermometer, the one we calibrate all our other thermometers off. Okay, latent heat. You might have seen the latent heat curve in other physics courses, but the latent heat curve looks like this. So latent heat is the heat that's required to convert a solid into a liquid, or the amount of heat that's required to turn a liquid into a vapor. So melting ice to water or boiling water to steam. But over that amount of heat exchange, there's no change in temperature whatsoever. So basically what happens when you're melting ice is once you get to 0 degrees, you need to keep adding heat energy, but the entirety of the body won't increase in temperature until all of it has been melted. And that's what this is basically saying. This is saying, okay, so this is the temperature, this is the time. So there's no temperature change over the certain amount of time until the entirety of it is melted, and then it goes off again. Okay, the specific latent heat, this is used in a lot of calculations. A specific latent heat of a body, or a substance should I say, is defined as the amount of heat required to change a unit mass. So we usually use the amount of heat required to change a kilo of a substance, so say a kilo of ice, without changing temperature. So the amount of heat energy you need to add here to melt the entire thing. Okay, heat transfer. So the 3 ways that we discuss in physics are conduction. So what happens is you have maybe 2 bodies in contact, and you might have 2 little molecules. One might be shaking. Now the shaking is vibration caused by the heat energy that's in it. So what happens is this one here on the left is shaking, and it's causing the one adjacent to it right beside it to shake a little bit. That's a transfer of energy over, so that's a transfer of heat. Convection, you might have seen this in previous experiments you've done. Convection is the movement of a fluid caused by hotter and less dense material. So less dense material is more spread out because it's hotter, there's more movement in it. That rises up, and the colder, denser material at the top will sink down. So that results in a transfer of heat. The heat moves upwards. We kind of see a spiral as they exchange heat as it transfers. Radiation, the transfer of heat energy, is electromagnetic waves. So think of the sun. The sun releases light energy, but it also releases energy in heat as well. So that has nothing to pass through in space, but it still reaches us. So that's radiation. The U value of a house. So these are the last few definitions we talk about in heat and temperature. So the U value of a house is the measure of heat loss to the surroundings. If you have a house that's usually really cold and needs a lot of heating, chances are it's got a high U value because it loses a lot of heat to the outside environment. Okay, U value of a material. Okay, so that's a measure of the heat flow through a meter squared of material every second. When on one side you have a temperature, and on the opposite side you have a temperature maybe 1 Kelvin lower, 1 Celsius lower. Okay, a heat pump is a device that extracts heat from one area and transfers it to another. Okay, so the important thing here to remember is you look at your fridge, it's cold inside and heat is being transferred from the colder part to the warmer part outside, but that requires energy. If you think about the logical thing that to happen here is that if you have a hot object, the heat will flow from the hot object into the cold object. So a fridge, to do the inverse of that, just needs to have energy going into it. You can never have heat moving from cold to hot without putting energy in to do it. More in-depth description of a latent heat curve. So when you're melting ice to water, for example, or boiling water to steam, the temperature won't change until all of the ice is melted or all the water is boiled. So if you look here, what we have happening here is the temperature that it melts at. So over time, it starts to melt just here. But until all of it has melted here, our temperature can't increase. So over time, time's still moving on, but the temperature isn't increasing because that's where the entirety of it is melting. Then it starts to heat up again, moves up to 100 degrees Celsius. If it's water, say for example, this is the temperature where it starts to boil. So that'll be 100 degrees Celsius for water. At that point, it all starts to boil, but until the whole body is completely boiled, we're not going to see another increase in temperature until over here, where it's fully boiled. Then that vapor starts to increase in temperature again. Equations we need to discuss energy conversion in heat, energy transfer in heat. The energy in some change of temperature is given by E equals m times c times delta theta. Okay, so, and if you're changing state, so in a latent heat curve, it's just given by m times L. Okay, above, m is just the mass of it, so how heavy your water is, for example. C is the specific heat capacity, so if you look back, it's the amount of energy you need to put into a kilo to change it by 1 Kelvin. Delta theta is just a difference between initial and final temperature. If you're heating a body of water 10 degrees, that's your change in temperature, so your delta theta would be 10. You can get that, say if you're starting at 20 degrees centigrade and you're going up to 30, that's a difference of 10, so you just subtract the final minus initial. And finally, L is the value for latent heat of fusion or vaporization. Hope the video was helpful. Give me a like and subscribe, and comment below if you want some more of these videos.